This is the lab finding the rate law of crystal violet using Beer's law by Natalie .antenucci and Ben Braden. The first step is to determine how to prepare the dilutions of crystal violet. We found the volume of crystal violet by using the formula M1V1 equals M2V2. The chart shows the varying molarity based on the volumes of either distilled water or sodium hydroxide, depending on whether we were using it to create the calibration curve or the actual reaction. Once we found the amount of crystal violet needed in each solution, we had to create a calibration curve. First, we had to determine what wavelength we wanted to use for the experiment. We were looking for a wavelength which gave us an absorption of no more than 1. Using the graph shown, we found the wavelength that we would use to create the calibration curve at 565 nanometers. We then drew a straight line down from the curve to the x-axis. We used this line to estimate the amount that the dilutions would absorb. We found that the 20 micromolar solution would be best due to the fact that it was a little over 1, so when we diluted the solution, it would fall at an absorbance less than 1. To create the calibration curve, our group used the data we gained from the pre-lab to make 5 solutions of crystal violet in distilled water. We then put these solutions in the colorimeter and tracked their absorption. Shown on the table are these absorption values. We used this data to construct the calibration curve shown. The curve further proved that we should use the 20 micromolar solution because its absorbance was closest to 1 without going over. In order to calculate molarity, which we will need to construct graphs and solve for the rate law later in the experiment, we will have to use Beer's law. We know that the equation is A equals EBC, where A is absorbance, B is distance that the light travels to the colorimeter, C is the concentration, and E is the absorptive constant. Because we are solving for the concentration, we can put the equation in terms of C. We can get rid of B because in this experiment, B is equal to the width of the cuvette, which is 1 centimeter. A and C are directly related, so you know that E is the slope of the calibration curve. In our case, E equals 0.036. Next, we did the reaction between the 20 micromolars of crystal violet and sodium hydroxide. We diluted the crystal violet to the molarity we wanted by using 8 milliliters of CV and 2 milliliters of NaOH. We used the colorimeter to track the absorbance over time as the reaction took place. Here is a sped up clip of the reaction happening outside of the colorimeter. The data shown is the absorption of the colorimeter over a 5-minute period. The table shows a data entry every 12 seconds. We then graphed this data over time. We used Beer's law, which was shown earlier in the video, to convert absorption to molarity. We then created a few graphs using molarity to determine the rate law. The first graph shows molarity versus time. If this graph was a straight line, we would have known that the reaction was 0 order. This next graph is 1 over molarity. If this graph would have been a straight line, the reaction would have been 2nd order. This graph shows the natural log of concentration over time. We know this is the correct graph because it forms a straight line. This means the reaction is 1st order. The equation for this line is located in the title. Next, we solve for the rate constant. We use the equation which relates the concentration of a substance to the rate log constant in order to solve for said constant. We chose to plug in the data for the reaction at 300 seconds. Solving the equation out after we plugged in the concentration at 300 seconds and the concentration at 0 seconds, the final rate law we got was the rate is equal to 0.004777713 seconds to the negative first times the molarity of crystal violet to the 1st power. One of our possible sources of error could have been scratches on the outside of the cuvettes. The cuvettes were plastic and could be scratched easily. Scratches on the cuvette would cause the absorbance to be higher, which would make our recorded value of the molarity higher. This could be corrected by using a new cuvette. We could also try using a quartz or glass cuvette to prevent further scratches.